step in being able to approach a BGP is understanding all the different aspects of the all work together. In order to be able to do that, we're going to first go over neighbor relationships because they're different than we've seen in other protocols, BGP message types, and obviously the route exchange and selection process. First, we want to understand neighbor relationships. And the graphic you see to our left is actually from our lab environment, router 1 and router 6. Router 1, if you recall, we used as the head end for our EIGRP part of our lab. And router 6 was the head end for our OSPF lab pod. Now, what you see here that's not in the diagram we've looked at before is an internet router that's actually going to be supplying some additional routes so we can actually see how BGP processes different things. But it's important to understand how BGP establishes neighbor relationships. Unlike other protocols, they do not have to be on the same subnet. In other words, they don't have to be directly connected. They can actually be several hops apart. This is always true in iBGP and frequently true in BGP, or eBGP rather. Instead of having a distinct protocol type in the IP header, BGP uses TCP to be able to establish neighbor connectivity, and this is actually accomplished on port 179. Instead of using different discovery mechanisms through multicast, peering sessions are actually established through unicast sessions, and in fact have to be manually configured. Again, there's no dynamic discovery process. The network command, as you've seen it used in OSPF, EIGRP, and even routing information protocol, do not have the same function in BGP. Neighbor configurations have to be done manually. For instance, router 1 that's pictured to the left would actually have to manually configure relationships with the internet router at the top and router 6. Once those relationships are established, these peers, and peer is just another word for BGP neighbor, peer and speaker are both sometimes used interchangeably, they actually advertise prefix and length data, and it's called NLRI, or Network Layer Reachability Information, when it's used in BGP. And instead of using traditional metrics to be able to do route selection, there are a whole host of decision points called BGP path attributes, which we'll look at later. Now, as BGP peers are actually establishing the relationship with neighbors, it passes through several states. Now, this is not West Virginia and North Carolina. It's actually different stages, you might say. The first stage or state is idle. It means the process is down or it's inactive. You'll frequently see this when you first configure a neighbor relationship. The next is the connect state. It means that the TCP connection establishment is in the process of being connected. Active means that the TCP connection is established, it's up between neighbors, but no BGP messages have been sent to the peer. Open sent is TCP is active, the open message is sent, and that particular router is awaiting the matching open message from the other router. Then there's open confirm, which is the open message is sent and received, and the BGP keep alive or notification messages are what's being waited on. And then finally, the last state is established. This is actually the desired neighbor state for BGP neighbors. It means all the peer settings, they match, the neighbors are connected, and the process of being able to exchange BGP messages is now possible. Now, in the normal process of the neighbor establishment, this process actually goes very quickly. Granted, if the BGP timers are 60 seconds, 180 seconds, and so forth, it can actually take a lot longer. In fact, in a lab environment, you probably want to shorten those. But if the process does not go to established very quickly, for instance, if it's stuck in idle or active, you need to make sure that you look and make certain that there is not some misconfiguration going on. So if the neighbor relationship gets stuck, always do that first. BGP peers actually have several requirements in order to be able to establish a relationship. The autonomous system number that's configured on the local router has to match the one configured on the neighbor command on the peer. Now let me explain that a little bit. In our graphic, router 1 is in autonomous system 65001. So the process would be started with router BGP 65001. But then in order to be able to configure a neighbor relationship under that process on router 1, you would type neighbor 10.99.99.6 because that's router 6's IP address, remote AS, and then 65006. On router 6, it's the opposite. It's router BGP 65006 and then neighbor 10.99.99.1, remote AS 65001. So you see they're inverses of each other and they have to match or the neighbor relationship will fail. Same thing with the IP address, as I mentioned. The router ID numbers can't be the same. So if you've manually configured, let's say 10.1.1.1 on router 1, and you try to configure 10.1.1.1 on router 6, the neighbor relationship is going to fail. They have to be unique. Now, if you're just using the peering IP, for instance, 10.99.1 and 6 respectively, then it's not likely to be a problem. But just keep that in mind. If you're using neighbor authentication, you have to make sure those strings match. It's the same as with the other protocols we looked at. So these are some things that are requirements, or the BGP neighbor relationship establishment will fail. Now, on the subject of router IDs, it's important to understand how BGP actually chooses router IDs. Obviously, the first preference is if you've manually configured it using the BGP router ID command under the BGP routing process. That's always going to get first crack. If there's no router ID specified, BGP is going to use the highest configured loopback address on the device. So you want to make sure, if you have multiple loopbacks, that the one that you want to be able to become the router ID, if you're not going to specify it, it's going to be that highest one. If no loopback interfaces are configured at all, BGP is going to choose the highest functioning configured interface address on the device. So keep that in mind as well. So router ID, configured router ID, highest loopback, highest interface. Now let's delve a little bit into BGP message types. We talked about the different types of messages that BGP routers send to one another. It uses 4 primary types, and again, this is all taking place on port 179 of TCP. One we already talked about a little bit before is the open message. It's very similar to the hello messages in the interior gateway protocols we've already looked at. It establishes the relationship, and it transmits neighbor settings. The second message is keep alive, and essentially the open and keep alive messages both together act similar to the hellos on a lot of IGPs, but it is a separate message. It's used to detect the fact the neighbor is still up, alive, and functioning and ready to be able to pass traffic. If the keep alive messages keep flowing, then the update message is used. This is the exchange of network layer reachability information, prefix and mask data for route calculation purposes. This is all the exchange of essentially routes that the router knows about. And then there's notification. Notification is an error message. If everything's functioning as it should be, you shouldn't see notification messages. It should be a matter of seeing keep alive, update, and open messages if the relationship is being established. But these are the 4 primary message types used in Border Gateway Protocol. To exchange routes, again, this is network layer reachability information. There are no traditional metrics as we've seen in OSPF, Routing Information Protocol, and EIGRP. There are actually path attributes which are used for calculating the best route. And there are 4 basic classifications of path attributes you should be familiar with. The first type of category is well-known, and well-known mandatory and well-known discretionary. It's actually these are 2 categories, but it's easier to group them this way. Well-known attributes are required in all BGP implementations. In other words, it has to be a part of how Cisco writes BGP, or Juniper, or 3Com, or HP, or whomever. It has to be included in the update messages. Mandatory means it has to be included not just implementations in the update messages, which we talked about just a moment ago. Discretionary means maybe it'll be sent, maybe it won't. So that's the well-known mandatory and well-known discretionary. Optional means it's not required in all BGP implementations. So it's not necessarily something you can bank on a function that may be working. And of the 2 subtypes of that, there's optional transitive, which means that attributes will be passed on to the BGP neighbor, and non-transitive means just ignore them. So the 4 types are well-known mandatory, well-known discretionary, optional transitive, and optional non-transitive. Now the well-known mandatory attributes, now that we've looked at the categories, let's actually drill down into the specific path attributes, well-known mandatory attributes. The first is called the origin attribute, and it basically says where the route was learned from, what the source is. Now, it uses several codes to actually be able to communicate what that is. The first, signified by the lowercase letter I in BGP, means it was learned from an IGP. This is the highest preference. It's always going to be the most preferred one of anything. And it means it was learned from an IGP routing table, but injected into BGP manually through the network command. The network command is one way of actually being able to announce routes within BGP. The second origin code is E, or EGP. If you recall from our discussion about design principles, EGP was the predecessor of BGP. It's no longer in use, and essentially you're not going to see this, but this is the second preference. It was learned from the EGP protocol. And the last is incomplete, which is signified by a question mark. It doesn't mean that it's incomplete in the sense of, that it doesn't have all the correct attributes, but it means that it's unable to determine how the route was learned. And this is typically what you will see when a route's redistributed from another routing protocol. So IGP number one preference, EGP second preference, and incomplete is signified by the question mark. This is the origin attribute. The other well-known mandatory attribute in BGP is the AS path. It means essentially what are all the autonomous systems that this particular route has passed through. For instance, when you look at routes being propagated from router 6 to router 1 and the internet router, router 1, it's going to list the different autonomous systems that it's passed through. Router 6 will just simply pass 65006, and that'll essentially be all the autonomous systems that it's talking about has passed through. Now, and this happens actually, routes pass through the internet router and then to 65001 router 1 from router 6, you'll see 65006, 6500, and that's the AS path. If there were 27 different autonomous systems that it passed through, it would list all of those in order. So when a BGP router advertises something, it adds its own autonomous system number into the path. Now, there is a situation in which you can artificially lengthen the path. For instance, if you wanted all the traffic for router 6 to come through the internet router, you could actually do what's called prepending. It artificially lengthens the path. So you could just prepend a couple of extra numbers, and then suddenly the path through the internet router seems much more preferable because it's shorter than the one coming from router 6 to router 1 directly. The rule of thumb with BGP path selection using AS path is the shorter AS path is always going to be preferred. The final well-known mandatory attribute is next hop. And this actually, as you would think of with most routing protocols, is just talking about the next hop IP on the way to the destination network. Now this is where iBGP and EGP are important to understand the distinction. For external eBGP peers, the address is that of the advertising router's interface. So in this case, if a route's being advertised from router 6 to router 1, the next hop IP address is going to be router 6's interface. For internal or iBGP peers, the address is going to either be, if it's coming from within the autonomous system, one of the other iBGP routers, it's going to be that of the advertising router. If it's outside the autonomous system, it's going to point to whatever external BGP peer it's coming from. So that's an important distinction in how the next hop attributes actually listed in BGP updates. Now on to the well-known discretionary attributes. One, and it's used frequently, is called local pref or local preference. And this is a path attribute that's used within iBGP. It basically says when there's more than one way out of an autonomous system, for instance if you're multi-homed, it signifies which exit point to use. So if in the case of our little diagram up here, these are all eBGP routers. But if router 1 and let's say there was router 24 were all a part of AS number 65001, you could tell the system using the local preference attribute whether to use router 1 or the other router. It basically puts the degree of preference for a particular route. You can actually split some routes to exit the autonomous system on one device and others to exit it on a different device. This is one of the ways load balancing can be set up. It's also sometimes described as designating the preferred exit point for outbound routing. Local preference. Another well-known discretionary attribute is called the atomic aggregate, which sounds like probably some sort of superhero costume or designation, but it's actually talking about that somewhere along the way a route has been summarized or aggregated and some of the AS path information involved has been lost. So in other words, we talked about how the autonomous system path, the AS path, has all the autonomous systems listed. Well, there may be one particular system where a number of routes have been compacted down into one entry, which of course is preferable from a routing standpoint. But it says that, well, there's some information that may have been lost because this route was compacted by this particular router. When it does that, it lists also something called the aggregator attribute, which we'll talk about in a second, which essentially is the router that did the aggregating and might have information on the lost path information. It also can imply that that particular aggregated route may not be the most optimal path because there's information missing from the decision-making process. So optional transitive attributes. The first we talked about just a minute ago was the aggregator. This is the router ID of the router that did the aggregation. It's used optionally with the atomic aggregate path attribute. Another and frequently used optional transitive attribute is the community attribute. There's actually an entire array of things you can do with the community attribute, but it basically means that that particular router is part of a group with some common properties. And there are some commonly used ones. For instance, internet community means it's a default value and you can advertise it to whomever you want. There's no export, meaning it should not be exported outside of the autonomous system. It means don't advertise it to eBGP peers. The no advertise means don't advertise it to any BGP peers. The local AS community attribute means don't advertise it to eBGP peers either within or another autonomous system or confederation. Confederations are something that you can use between IBGP routers within an autonomous system. It's way beyond the scope of what we're going to talk about in the CCNP, but wanted to at least talk to you a little bit about it in this scope. An optional non-transitive attribute is the multi-exit discriminator. And this is a path attribute that tells, it's sort of the opposite of local preference. It's not talking about the preferred exit point from an autonomous system, but it's announcing to neighbors the preferred ingress point for the autonomous system. It's advertised to eBGP peers. When you see the word metric within BGP, it's not metric as we've traditionally thought of it, but it's actually a numerical value for the multiple exit discriminator. The default value is 0 and the lowest value is preferred. For instance, with local preference, the higher number is preferred. In the multi-exit discriminator, the lower number is preferred. And it's again, the entry point into an autonomous system. The originator ID cluster list, also optional non-transitive. These are used by IBGP route reflectors, which is something else that you can use in place of confederations. But again, it's way beyond the scope of what we want to discuss, but I wanted to at least mention that that's how those attributes worked. The final attribute, and it's not technically a path attribute, but it's actually a Cisco proprietary setting called wait. And wait is used, it's local only to a particular router. So for instance, with local preference, it's all within an autonomous system between IBGP peers, but wait is only on a particular router. It has no value to be communicated with other peers. The values are between 0 and 65535, and it's always the first thing that's looked at in the route selection process. Now, some default values is if the route is originated locally, the wait is set at 32768, and routes learned from other peers are automatically set at 0. But this is a way you can actually point to exit points from the standpoint of an originating router. It's local to the router. So we've talked a little bit about path attributes. Now we're just going to talk a little bit about how route exchange is done, the network layer reachability information. Obviously, as we talked about before, the BGP neighbors go through the different stages, finally reaching the established state. And once that happens, update messages are sent to build the BGP table, which is also called the RIB, or routing information base, as we talked about earlier. All learned routes are placed in the BGP table regardless if they're the best routes or the chosen routes. When you do a show IBGP command from the exec on the command line, it'll actually list all of the learned routes, even the ones that aren't necessarily considered best path. Once those are in the table, different path attributes are used in the transmitted updates depending on the type of different path attributes.